So with this we come to our second class. So basically in the previous class we had discussed about regression. What is regression? So briefly, can anyone tell me on the basis of the previous class that what do you understand by regression? Don't go by the definition which is shown on the screen. Explain it in your own words.
Yes, ma'am. So, ma'am, basically in the last class, we have been told about like how to minimize the, we have to find the value of M and C so that the value of the Y cap should be minimized according to the data set.
Is it really Y cap that you minimize?
No, like YI.
Is it YI? Would you like to reconsider your answer?
Error.
Yes.
Error,
exactly.
error, ma'am.
The error, the sum of the error should be minimum. Not just the error. Error is individual. Ith data point, each value is the error. So again today we will come to the cost function estimation. So that will give you a better idea of what do you understand by mean square error or mean absolute error or root mean square error. What are these errors? You will understand in details. But for now, just understand that regression is basically, you fit your given data set, whatever given in MLC, anything and everything is based on existing data, right? You have a given data set and you make predictions on the basis of that data set, right? So any kind of fitting, it need not be linear only. It could be any function fitting. It could be logarithmic. It could be exponential. It could be polynomial. It could be n number of any kind of function that you fit in your given data set. It will give you a predicted data for any given variable, right? Say suppose you have a set of x and y, which is your given data set, and you fit a best fit function there. And now using that function for any given x, now you can find out your y, right? So this is how you do the prediction based on a given data set. So this prediction is basically nothing but your regression. Now briefly, which we understood in the previous class, that was basically linear regression, which is the simplest form of regression that you can do, right? So another type of estimation that you can do using ML is classification. Okay, classification does not mean essentially prediction of values or data sets. It means categorizing. There are n number of discrete sets. In case of binomial, there will be two options and you have to either choose A or B. So this is categorizing. This is not regression. You are not predicting a value. Essentially, what you are doing is you are sorting it into a vivid set. Do you understand the difference between regression and classification now?
Yes.
Is there any doubt? What is the difference between regression and classification?
Madam, can you say one more time?
Okay. Regression means prediction of values based on your given data set. Whereas classification means based on your existing data set, you are predicting the boundary so that you can sort your data on different discrete sets. It does not essentially mean that you will be able to predict for a given value what is your function's value, but you will be able to classify which set it will belong to. So there is this difference between regression and classification. Do you understand now?
Yes, ma'am.
If I have to explain this with the help of an example, I will do that also. By regression, what we have discussed in the previous class, you are well aware of what we have done in the previous class, right? Just a minute. For example, this was linear regression, right? Yes. So these are your given data sets and this is your linear regression line, right? Now, on the basis of this given data set, if you are able to generate the equation of this line, this best fit curve, if you are able to generate now, once you have this curve, then for any given x value, you will be able to find out the y value because now you have the equation of the line, right? So this is what is regression. But suppose I was to do classification. So on the basis of these points, suppose I have a couple of red points here and a couple of green points here. Now I draw a line something like this. Something which is dividing these two zones. So now any point in the vicinity of this zone will be red, and any point in the vicinity of this zone or towards the right of your predicted line would be your green, right? So now you have been able to sort it on the basis of an imaginary line, the imaginary boundary that you've drawn. So that is called classification. So classification and prediction is not same, mind you. So this is the difference between regression and classification. I hope I'm clear right now. Yeah. Is there any doubt?
No, ma'am.
Okay. Okay. So now that you've understood that, we will go through a couple of problems in the first assignment, which goes through this classification and regression. Okay. So the first question was, which of the following are classification tasks? Could you answer this?
Predict the gender of a person by analyzing his writing style.
Okay, good. So that is the answer. A is your answer. Why is B not the answer?
It is a continuous value.
It is a continuous value. It is not a discrete set. Price is an actual figure that you can predict based on regression, right? Based on certain parameters, such as, your x1 could be floor area, x2 could be number of rooms, and so on and so forth. So based on your variables, you could predict your y value, which is price of a house, and that is not essentially a category. It is actually a value that you're predicting. So it falls under regression, not classification. What about C?
See regression.
Why is it regression?
Ma'am, temperature
Predict
itself.
the temperature. Temperature will predict.
Yeah, it is again a continuous set of values. It is not a discrete category as such. It is a value which you can predict based on parameters, right? What about D?
This is also regression.
Exactly. D is also similar to B and C. D is also again a regression based problem, because again the number of copies is a figure, which is your function y, which could have a continuous set of values, any value that could be predicted based on the independent variables that you choose to predict, right? So again, this is a regression problem, not a category based or classification problem. Let us come to question number 2. Which of the following is not a categorical feature?
Ma'am, the height of a person.
Okay, why is it so?
Ma'am, because height of a person is a continuous value, so we have to use regression here.
Exactly. Gender is again a categorical feature, right? You can have discrete sets. Types of mountains, again, types is a discrete feature. Nationality is a discrete feature, whereas height has a continuous set of values, any value it can take, right? So again, this is a regression based problem, whereas A, C and D are classification based problems. What about this one?
A.
E.
Why do you say that?
It's an algorithm based problem rather than a prediction problem.
Exactly. See, machine learning essentially means that you are not feeding any logic into your machine. The machine will learn on the basis of your given data set what it is supposed to give as the output. And once it learns, then without any supervision, without any assistance, it will be able to generate the output, because now it has programmed itself. Even if you directly feed an algorithm to your system and then generate the output, that is not machine learning. You are feeding the logic. For example, if I teach you how to add two numbers, say suppose 2 plus 3 is 5. So I'm teaching you how to add two numbers. In that case, I'm teaching you the logic of how to make the sum of those two numbers. I'm not letting you generate a logic of your own, right? I'm feeding you the logic. Do you see the difference? If I would have given you the set of inputs, that is 2 and 3, and the set of output, which is 5. Similarly, another set of data set, say suppose 7 plus 3 is 7 and 3, and then the output is 10. And then similarly, so on and so forth, I give you hundreds of examples. Now you, on the basis of your intelligence, if you can figure out that, okay, the logic between the input and output is summation, that is machine learning. You are learning on the basis of your input and output. But on the contrary, if I was to feed you the algorithm, if I was to teach you how you are supposed to add, then that is not machine learning. That is feeding the logic. Do you understand the difference between algorithmic learning and machine learning?
Ma'am,
Yes.
under which category does graph neural networks come, ma'am? Because graph neural networks is also, I believe that graph neural networks is also a part of machine learning. So using graph neural networks, we can find the shortest path distance, I believe. So under which category does graph neural networks come? Because we use graph neural networks to find the shortest path, in fact.
Yes, we do. But if it is a supervised, if you learn ahead, then you will be able to find the difference between supervised learning, there is unsupervised learning. So all these things are intricacies are there. What basically I want to tell you here is, unless it is an algorithm that it has to develop on its own, it is not a machine learning task. If you are to feed the logic, it is not the machine learning task. Essentially, this is nothing. Section A, the option A, is nothing but an optimization problem. If you see, right? Is there anyone who has studied optimization in their undergraduate courses or something?
Yes, sir.
Okay, so it is an optimization kind of problem, and you basically devise a formula for this. And once you devise a formula for this, you are finding the algorithm for this, then it is not a machine learning task. Whereas if you would have here, according to this option, what is your input that you are giving? What is the input? You are giving a pair of nodes, right?
Yeah.
Yes, ma'am. Yes,
Yeah.
yes.
So if you are giving a pair of nodes and there is no other constraint that you're feeding it there, then it is automatically implied that the straight line joining the pair of nodes will be the shortest path, right? So this is not something that is a machine learning problem. Whereas if you see the other problems, then you will be able to categorize them as regression or categorization. Now further, when you go ahead and learn what is supervised learning, what is unsupervised learning, all these aspects, then you will be able to relate regression problems with them. For now, you can understand that this is neither a regression problem nor this is a classification problem. This is a formulation-based problem.
Madam, what I'm asking is, means like in case A, like some algorithm is required. Right. But in case in machine learning, algorithm will be required, I think. Without an algorithm, how the input
this
will
is not the algorithm that you're talking of coding, the algorithm that you feed in your machine. By this algorithm, I mean this should have a formulation, a formula of its own. The algorithm that you refer to is the algorithm of your code, right? That you feed into your machine. We are not talking of that algorithm. By algorithm, I mean the protocol that you have to define, the formulation. You have to have a function defined here, basically. And that function, you have to devise a function which you will be able to optimize. And then by some optimization route, you are able to find the shortest path or whatever, the minimum value, basically, for that optimization function. See, once you devise a function, a formula for that function, then it is very easy to devise the minima of that function, right?
Right.
So devising a formula is not essentially a machine learning task per se. Machine learning essentially means that you are supposed to provide the inputs and the outputs, and it is supposed to train itself from the set of inputs and outputs. And once it is trained itself, then you will provide a set of testing inputs, and you will see what are the outputs, right? So that is what is essentially machine learning. You are not supposed to feed the logic. You are only supposed to train it. It is supposed to figure out on its own. If you feed the formulation itself, then of course not.
Means machine learning means I should have an input data as well as I should have an output data, means what will be the output.
A training set.
And then the training set. And then this entire process will be trained itself by the machine.
Exactly.
Then prediction means how it will predict. Prediction means something which have to predict a future.
Yes.
So if I have an output, means that's my prediction. This is what I'm predicting, and I have to check whether this comply with the input data.
Yes. So you have a
This-
testing
this-
set, you have a training set. All these are there. Ideally, 75 to 80% of your data is your training set. The rest is your testing set.
Right.
So you don't use your entire training set as your, entire data collection as your training set. You use a part of it for training, and then the remaining part you use it for testing. It's to check how optimized your algorithm has been. And in this case, the algorithm means the program that you have written, not the formulation of your problem.
That's it.
Okay. Is there any more doubt?
Option D is not an unsupervised and supervised learning, no?
You will get into the intricacies of this in the future lectures, but in the current state, what this option means, essentially no. It is not a machine learning task.
Okay.
Okay. What about option B?
Ma'am, it is a machine learning task.
Yes, it is a machine learning task. Which category will it fall in? Will it be-
Regression.
Regression, ma'am. Regression.
Yes, regression.
Is there anyone who does not comply with this answer?
No, it's regression. B is regression.
B is regression. Would you like to reconsider?
It's a classification because rise or fall. There's no continuous value.
There is no value that you're predicting here. You're just predicting whether it will rise or fall. So it is categorization, not regression.
Okay.
Regression would have been, it would have predicted the value of the stock price. What is the problem here? Whether it will rise or fall. Only two categories. Not the value of the stock price.
Yeah. It's classification.
Okay, what about C?
This is regression.
This is regression. What about D?
This is classification.
Classification. Very good. So now that you've understood this, we will move to the loss function and cost function. I was told to make a video on this one, so we will cover this aspect up briefly. So what do you mean by loss function? Does anyone know?
Error.
Error, exactly. So error of the whole function or a particular data set?
Of a particular data.
Of a particular data set. Okay, so I've got this data set, okay, and this data set I want to fit it into a say linear curve line, straight line. Okay, so my function which I want to fit is a straight line, and I want a best fit straight line for this. So I will give it 2 trials here. You can give it n number of trials. So what I will do here is I will make a copy of this data set and I've kept it here. Okay. So now that I have these 2 data sets, which is the same identical set of data, I will draw straight lines here and see how good they fit. Okay. So I have a straight line here and I have another straight line fitting the same data set here. So do you think the error in both the cases will be same?
No.
No.
Not really, no. So what will be the error? Can you see the difference? These are the errors in this case, whereas these are the errors in this case, right? So any kind of line that I fit into this data set will have its own individual errors associated with it, right? And each individual ith data set, in this case, the first data set is this one. In this case, this is your first data set, right? So your first value will be error 1, sorry, this should also have a subscript. Error 1 equals to y hat. Suppose I am referring to all the values in this line as y hat and all the values in this line as y bar. Okay. And all my original values as yi. Okay. So y hat 1 minus y1 is the error associated with your first data set in this configuration, in this line. Whereas in this line, in this case, your error 1 is larger than the previous case. Here your y bar 1 minus y1 is your error. error 1 associated with this line. So first case and second case, if I check the error 1 value, then evidently my error is larger in the case of second case. So far so good? Understandable?
Yes, ma'am.
Please repeat.
Okay. So I will just focus on the first data set in both the cases. I have the same, see, I have the same data set. This and this is identical. Okay. So I am fitting two different lines. One is this one and one is a steeper slope, this one. So I've tried to fit two different lines. You can draw infinite number of lines with infinite number of slopes, but here I have chosen two examples just to illustrate. Okay. So I've drawn a line here and I've drawn a line here, and with all of the points I've drawn the error magnitudes. Yeah. So far so good? Is there any confusion?
No.
Okay. Okay. So now that you've understood this much, I'm talking of the individual errors associated with each of the points. Okay. So I have I number of I equals to 1 to I equals to n number of points here, right? So this is my 1, this is my second data set, this is my third data set, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah. So I have 19 data sets. So I have I equals to 1 to I equal to 19 data sets available here, right? So for each of the 19 points, I have their individual errors associated with it. For this configuration, again another line is drawn here. So for this configuration, I have a different set of errors associated with all of the points, right? So I've just taken the difference of these values. yi was my original data set, whereas y hat I is on this line, all of the points that lie on this line. Y bar I, all of the points that lie on this line. So far so good? Understandable?
Yes, ma'am.
Yes, ma'am.
Okay. So what is the error associated with each point? Essentially, it is nothing but the difference between the two, right? This is my y1 and this is my y hat 1. So what is the error associated with it? Just the difference associated with it, right? Similarly, this is my y2, this is my y hat 2. So this small line, red line, is your error associated with it, and so on and so forth. Similarly, here also, my yi is here again, and my y bar I is here. So what is the error associated with it? Yi minus y bar I, or vice versa, whatever you do, just the magnitude. So this is the error associated with it, and just by eye estimation you are able to see very vividly that your error 1 for this configuration and error 1 for this configuration, if you compare, then the second case your error 1 is larger. Can you see that?
Yes.
Okay. Again, the last point, the 19th point, if I see here also, your error 19 and error 19 of this line, if you compare, then the second case is larger. Followed me so far?
Yes, ma'am.
Okay. But does that mean that all of the cases this place we find the error is larger? No. There are other points where the error is lesser than the previous configuration, and here also there are other points where the error is larger than the second configuration. So essentially, what do I want to minimize? Is it the individual error or is it the total error?
Total error.
Exactly. I want to minimize the total error, not the individual error. But when you are talking of each individual error, you are basically talking of the loss function. So see, error is briefly defined as, the difference between the two. But if you want to talk of loss function, then loss function essentially means that you can define not just the magnitude of the error, but also you can take a square of it. You can take a weighted square of it. See, you have a particular, point here, right? And there is a point here also. Compared to this point, if you want to see, if you zoom in, what would you see? Is this point closer to the line or this point closer to the line?
Ma'am, the first point.
First
The
point.
first point is closer to the line. So if I were to take not just the error but a weighted error, weighted loss function, would it and I was to give more priority or more weightage to the one which is nearer and less weightage to the outliers or the ones which are farther, then do you think that the loss function magnitude for this and this will differ by the same amount, or will that difference increase? I will repeat my question again. See, there is a difference between this point and this point, right? Say suppose I was to compare the error, which is the difference between the two, right? So this length and there is this length. So the difference between the two is just the algebraic difference, nothing else. But if I were to associate a weight with respect to the distance between them and the corresponding point on the line, which is the vertical perpendicular that you throw from this point to this line, then do you think that this difference will suffice as the error, or will that difference increase?
Increase, I think so, ma'am.
Exactly, it will increase. It will increase because you are giving weights now. Say suppose this one is closer to this. So suppose I give a weight with respect to its distance. So suppose whatever distance this point is from this line, this perpendicular distance, this point is exactly double. So the weight that this point will get is exactly double than this point, isn't it?
Yes, ma'am.
If I give this point as weight 1, then I am to give weight half to this point. If I were to give weight 2 to this point, then I will give weight 1 to this point, exactly half. So now it is not just a simple error value, it is also a weighted error value. So you can define your loss function depending on your data set or your understanding of your variables, on understanding of the problem statement, on understanding of the experimental values that you get. A lot of things. On the basis of a lot of things, you can define n number of types of loss functions, and you can designate each error value. So error simplistically means is just the difference. But if you're talking of the loss function, that is again for individual data set, but it is not essentially just the difference. It could be the difference, it could be the square of the difference, it could be the modulus of the difference, it could be a function of that difference, it could be weighted function of that difference. So it could be anything, but again it is associated with each individual data set. The moment you sum up all your loss functions, it will give you the total cost function, and essentially that is what you want to minimize, not individual loss function or not individual error. You want to minimize the total error or the total cost function. Is that understandable?
Yes, ma'am.
Is there
Yes,
any
ma'am.
confusion?
Yes, ma'am.
Any
Yeah, it's
confusion?
clear.
Ma'am,
Yes.
ma'am, actually I want to ask y bar, the point where the which of the y bar point is present. It is present on classifier or on the side or on the space.
Y bar lies on this line. See, essentially y bar will satisfy the equation y bar equal to mx bar plus c, and y cap will satisfy the expression y cap equals to mx cap plus c, and this m and c and this m and c will be different. For both of the lines, the slope and intercepts are different. Okay, so but then y cap I should satisfy, because it is lying on this line, any point lying on this line should satisfy its equation also, right? So if you briefly see, for example, this point is yi, and it is also lying on this line, so it is also y cap I. So the difference will be 0, error will be 0 here, because yi and y cap I are same. But if you see other points, for example, this point is your yi, and its corresponding point on the line is y cap I, which is here, and the difference is not 0. Can you see that?
Yes, ma'am.
Right? So any point which lies on this line should be y cap I. Any point
Yes,
which
ma'am.
lies
That means error equal to prediction minus actual.
exactly, yes, that is what is error. Now it's clear.
Thank you.
Okay, so now if no doubt is there, so I will just go ahead with designation. It is just a convention how you define it. So if you are talking of first degree difference, which is just the magnitude, the linear difference, there is no power associated with it, so it is called L1 loss function for any given data point. This is the first data point, so this is the I equals to 1 data point. This was the last data point, which is I equal to 19 data point. So there are n number of data points here, and for all those data points, this is how you can define your L1 loss function. Again, similarly here also L1 loss function. The formula is same, or rather similar, and here instead of y cap you just replace by y bar, because y bar are the points which are lying on this particular line. Similarly, L2 loss function, if you were to define, this is just a convention how you name it, it has nothing to do with the formula. So if you have a squared definition of your error, of your loss function, then you essentially call it as L2 loss function for the ith data point, and this is how you define it. And here you don't need a modulus sign. The square of your error is essentially positive, so summing it algebraically would also yield a positive value, and you don't need to worry about it nullifying the errors. But if you were to add this, then you have to put the mod sign, because if you don't, then algebraically it might nullify some of the errors, which are the positive ones and negative ones, and essentially you may end up getting zero error or near to zero error, which is not actually the scenario, right? So you need a real estimation of your error. For that you need to put a modulus sign if you were to add these up. So essentially the loss function, if you add them up, if you put a summation sign and I equals to 1 to I equals to 19 or I equals to n, whatever is your number of data set, so that will give you your cost function. So cost function is nothing but the summation of your loss functions. Understood so far? How do you define your loss function?
Yeah, it's clear.
Okay, so we will move ahead to the next slide. So now about your cost function, you need to understand that your cost function, do you remember from the previous video or the previous lecture that we were talking of error function, and we were trying to minimize the error function to devise the values of your parameters m and c in your straight line equation?
Yes, ma'am. Root mean square we are minimizing.
Exactly, root mean square. So that is how you define your error. So there are various kinds of definition of your error. These are few examples, but again, like I said, you could have weighted loss function, you could have n number of loss functions, and based on your loss function you could define your cost function. These are few cost functions which you could define and try to minimize, and these formulations are shown here. So for example, if you have your error square and you take the average or the mean of it, so this is mean squared error. Again, what you have to do is you just have to go backwards. So you take the error, you square it, and then you take the mean, right? So that is your mean squared error. So essentially what we were minimizing in the last class was nothing but your mean squared error. If you take an under root of that, which we had also discussed in the previous class, then it is nothing but root mean squared error, right? So that is called RMS value. So what you do, again, you read it backwards. You take the square of your errors, you take a mean of that, and then you take the root of that. So that is your RMS value. It is essentially the same formulation but with an under root. Okay, there is another definition that you can do. Instead of the square, what you do is you just take the absolute values, which is your L1 loss function, summation of your L1 loss function. So this is this mean absolute error. Here instead of, so mean absolute error essentially means that it is a modulus of your error, and you take a mean of that. your absolute error value, and you take a mean of that. So basically, again, if you read it backwards, it is you take your error, you take the absolute value of those errors, and you take a mean of that absolute value. Okay, so that is essentially your mean absolute error. Again, to reiterate, I would say again, it is nothing but the summation of your L1 loss function. If you were to take a summation of your L2 loss function, it was a mean squared error. And again, the RMS value is nothing but it is associated with your mean squared error. It is nothing but the under root of your mean squared error. Okay, so far so good. You understand these cost functions?
Yes, ma'am.
Okay, so now that you understand the cost function, I will briefly illustrate how these problems vary in real life. So you take a first example. You have a starting point and you have an end point, and you have n number of paths associated with your start to end. Okay, and you know the duration that you would require to cross those paths, right? So if you were to minimize your cost function, what would it be? Which path would it be?
Shortest path.
Second one.
Yeah, which one? Second one, right?
Yes, ma'am.
Minutes.
Yeah, so the second
Yes.
path is your shortest path. It is evident from this diagram. But in real life, is the problem that simple? Is it just this start point and end point?
No,
You
ma'am.
have just this two? Not really. You would have something like this, or even more complex. This is still a very simplistic design, right? So you have a starting point, you have a stop point, but midway you have a lot of stopping points. Or suppose this is a bus route, for example. So bus route is not supposed to be a straight line from your start to stop, right? It will go from here to there to this to that. There will be certain stoppages, right? So if you were to now minimize this, is it the correct way to minimize just this distance and this distance on the basis of the nodes? For example, if I go from here to here via straight line, here to here, here to here, 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 and here, would it be the shortest path?
No.
Not really.
No.
It is possible that you take the longest path from start to this node, and then from here on you go from the shortest path, and that might end up being the shortest path. It is possible that from here to here you take the shortest path, and then from here to here you take the longest path, and you still end up getting the smallest total path. It is possible, right?
Yes, ma'am.
So it
Yes,
depends.
ma'am.
So what are you trying to minimize here? Are you minimizing the individual error, or are you minimizing the total error?
Total error.
Total error.
Exactly.
Total
So
error.
that is what is the difference between your loss function and cost function. Your loss function is your individual error. Say suppose if I were to minimize, the distance between this start and this node, then of course this would have been the shortest path rather than going from here to here or here to here. But if I were not to minimize from here to here, but from here to here, then I am not to look for this small loss function. I am to look for the total cost function. What is the total time duration that I need? And that should be minimized, right?
Yes, ma'am. So, ma'am, basically we can conclude that cost function measures a model error on a group of data instances, whereas the loss function quantifies how much a model prediction deviates from the ground truth for one particular data instance.
For one particular, yes, exactly.
Okay.
Well said. Okay, so is there any doubt now? What is the difference between your loss function and your cost function?
Cost is a group of cost function is a total error. Cost function is total error.
Yes, cost is your total error. Not really error, I would say total loss, sum of your loss function. When you say error, you are basically talking of just the difference. But when you are talking of the loss function, you could define it in a lot of ways. Okay, so that is a small exemplary difference that you can keep in your mind, just to, so that you can use the precise terminology for your illustrations. Do you understand the difference between loss function and your error?
Yes, ma'am.
So error and loss
Yes, ma'am.
function both are associated with each data point, ith data point only, not the total. But again, error is just the difference value, whereas loss function could be any function related to the difference of that value. It could be a square, it could be a weighted value, anything. It could be anything. It could be a modulus, like I showed here. So it is a function, loss function, but error is the difference. So you understand that, right? Is there any doubt here?
Yeah.
Okay, so with this we move to the final topic for today, which is the confusion matrix. So how many of you are aware of this concept, confusion matrix?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay, so can you briefly illustrate in 1 or 2 sentences what do you understand by that?
Is nothing but a pictorial representation of the predicted and actual value.
Okay, so nicely illustrated, but I will just elaborate it. So you have, say, suppose a classification case, okay, and in the classification case you are addressing the binary classification case, which is the simplest one. So let us, for the sake of simplicity, assume that you have 2 classification, one is positive, one is negative. Okay, you have 2 classifications. Your data set could be either positive or it could be either negative. So now there is your actual positive and negative values, which is your given data set, and there is this predicted positive or negative values, which your machine is predicting whether a given value is positive or negative. Your machine could predict correctly or wrongly, but we will tabulate that. One case is it is actually positive and your machine is also predicting it as positive. That is called as true positive. Another case is when it is actually positive but your machine is calling it negative because there is a flaw in the training. Okay, machine is not fully trained or whatever be the reason, it is calling it negative. So this is called false negative. Okay, there's another set which is if your actual data set is negative but your machine is calling it as positive. Again, this is a flaw and it is called as false positive. Okay, and again there is fourth case, which is it is actually negative and the machine is also calling it as negative. So that is true negative. So far so good, understandable?
Yes, ma'am.
So this is just a binary classification. You are dealing with a binary classification. It is either positive or negative. There is no third column or third row that we are talking of. So in this binary classification, you have these 4 classifications that could happen, 4 scenarios which could occur, right? Is there any other scenario which could occur out of apart from these 4? Is it possible?
No, ma'am.
Can you explain with the example?
Okay. So suppose you have a bucket full of red balls and green balls. Okay. There are no other color balls. It is either green or it is either red. Okay. So now I trained my machine to understand which one is red and which one is green on the basis of its size or density, anything, whatever my parameters are fine, anything. I train my machine. Okay, and now I pick a random ball from the machine, from the bucket, and I show it to my machine and it designates it either red or green. Now in this binary classification, it could either be red or green. Is there any other possibility?
No.
No. But suppose I pick up a red ball. What could my machine call it?
A red ball.
My machine, if it is trained well, it could call it red ball. If it is not trained well, it may call it a green ball. Is there any other possibility that it could call it any other color? Because it is not trained to call it any other color, right? It is a binary set that it has been trained on. So now my machine, if it is able to predict that a red ball is a red ball, then it is true positive. Now if I pick up a red ball and it calls it green, then it is false negative. Okay, suppose red is positive, green is negative, for the sake of simplicity, if you want to associate with this example. Then it is false negative. A vice versa case where I was showing green and it recognized it as red is false positive. And the last case where I was showing green and it recognized it as green, in that case it is true negative. Do you understand this classification case now?
Yeah, now it's clear.
Okay. So apart from this, there is no other scenario that could occur. So all the 4 scenarios are covered. So if all these 4 are the only things that could occur, that means my total set is this, the sum of this, true positive plus false negative plus false positive plus true negative. If I sum it all up, this should be my total universal set that I am talking of. So any fraction that I want to take, I will take with the denominator of this total summation. So far so good?
Yes, ma'am.
Now I want to find
Can you
out.
please repeat the last part once again?
Okay. So do you understand, for a given binary classification, these are the 4 scenarios that could occur and there is no other scenario that could occur?
Yes.
This part is clear. So if this 4 is the only thing that could occur and there are no other scenarios, that means this is the universal set that I am talking of. TP plus FN plus FP plus TN.
Yes.
This should be the total universal set that I am dealing with. So any fraction that I want to find out, the maximum denomination that I could have in the denominator is the summation of these 4 values. There could be no other thing. Right?
I have one question.
Yes. Go on.
I have one question. The total set would be only true positive plus true negative, because half of the values are the predicted and half of the values are true.
Not really. No. Your total set is not your object. Total set is your predictions that you are dealing with. It is not the number of balls that I am counting here. It is the number of possibilities.
Okay, understood.
You understand, right?
Can we say the probability of each happening is 25%?
Not really. No. If your machine is not trained, if it is biased, then if suppose your data set which you trained your machine on had say 75 red balls and 25 green balls, in that case it would have a bias towards red. It has more possibility of predicting red. Do you think it will have even percentage for all of the cases?
No. Yeah.
Not really. So it is not equal. It may be, it may not be. It depends on your bias of your data, bias of your training, whatever it be. Suppose the variables that you chose to train the machine on, those variables were biased. What about then? It could be anything. Your data set is not fair. It is a real-time data that you're feeding a machine. Understandable? Is there any doubt? You don't have to hesitate.
No confusion.
Okay, so if this is understandable, then I will go on to what are these terminologies that we call. Okay. See, sensitivity or recall is associated with your actual values, that is your denominator, and your true positive value, that is your numerator. This is sensitivity. This is also called as recall. So suppose there are a certain set of positives in your classification or a certain set of red balls in your bucket. Okay. Now your machine could predict the true positive values as well as some positive values it designated as negative values. It is possible. But all of this is actually red, is actually positive. Right? Your true positive plus false negative is the total actual positive value, or the total number of red balls is true positive plus false negative. Is there any more red ball in your bucket? No. So your actual number of red balls is what? True positive plus false negative. Out of which, how many could your machine predict correctly? True positive. So what is the recall or what is the sensitivity? True positive by the actual number of positives. Should I repeat again? Amongst the actual number of positives. What is the actual number of positives? This is the actual class C. So the actual number of positive is the sum of this total row, right? So actual number of positive is true positive plus false negative, right? Out of which, how many could your machine predict as positive? The true positive value. Again, if I want to put it in the color form, then this red, positive is red, negative is green, right? So out of the total number of red and green balls, how many red balls are there? These many red balls are there. The true positive and false negative. These many red balls are there. Out of which, how many red balls did your machine predict? The true positive value. So what is your recall or sensitivity value? The number of red balls that your machine predicted divided by the actual number of red balls that are present. Followed me so far?
Yes, ma'am.
Yes, ma'am.
Okay. Now let us come to precision. How precise your model is. How do you estimate that? Here, the denominator is not your actual class, but your predicted class. So, if your machine predicted certain positive values, how many of them are actually positive? Your machine predicted how many positive values? True positive plus false positive. And how many of them are actually positive? The true positive ones. So what is your precision? True positive divided by the predicted number of positives. If I want to put it this way, your machine predicted, so this is not the actual color that I'm talking of. Your machine predicted that these are your red balls and these are your red balls. But actually, how many of them are red balls? Only these. So what is your precision? The predicted actual red balls and the total predicted red balls. So that is called precision. Do you understand the difference between recall and precision?
Yes, ma'am.
Yes, ma'am.
Is there any confusion here? Any doubt? If there is any doubt? Okay. So if there is no other doubt, then I will move to this. Okay, the specificity and negative predicted value, again, you can associate with these two. So for the dearth of time, I will not describe these in detail. You will be able to associate them with the positives, right? So this accuracy, what is accuracy again? Accuracy means the true positive value and the true negative values. Rest are the mistakes. They are not accurate, right? So out of the total set, the actual positives, which it also called as positive, and the actual negatives, which it also called as negative. The true positive and the true negative are your correct predictions, whereas your false positive and false negative are your wrong predictions. So the correct predictions divided by the total predictions will give you your accuracy of your model. Do you understand this? Is there any confusion here? What is accuracy?
It's clear. Well explained.
Okay. So yeah, this is your fourth question in your first assignment. So you have 10,000 emails in your mailbox, out of which 200 are spams, right? Now your detection system detects that there are 150 mails as spam. See, this is your detection, your prediction, whereas these are your actual spams, right? Now your prediction detects these as spams, out of which actually only this fraction, this number are spams. So what is the precision and what is the recall?
Precision 33.33 and recall 25%.
And how so?
Yeah, A option is right.
Why? Could you elaborate?
Yes, true positive is 150.
True positive is 150.
Spam detection system detects 150 as a spam. So 150. Sorry, 50.
Exactly. So 50 is
And,
your true positive. Okay.
Yes. And 100 is true negative. 9,800.
50 divided by 150 and 50 divided by 200.
Exactly. 50
Yes.
divided by 150 and 50 divided by 200. So which are those values? See, 50 by 150 is what? Precision or recall?
Precision.
Why is it precision?
Because actually how much it is predicting.
No, not actually how much it is predicting. See, this is your precision, right?
Total.
So precision is this total value. It is predicting this total value as 150, right? These many it is calling as 150. The true positive and false positive as 150. So your denominator is 150 and true positive is 50. So 50 by 150. That is your precision.
Ma'am, excuse me.
Yes.
Ma'am, precision should be 50 upon 50 plus 150 now.
Why should it be 50 plus 150?
Ma'am, because true positive plus false positive and true positive is 50.
Right.
So then subtracted, if we subtract, then 150 will be remaining. So it should be false positive.
No. See, this is where you're getting it wrong. Read the statement correctly. The spam detection system detects 150 mails as spams. So it is detecting 150 as spam, which may be truly spams or which may be falsely spams. So this denominator TP plus FP is given as 150, not just one term.
Yes, okay.
So you don't need to add anything more there. This is already given as 150. You don't need something else.
Madam, so 150 is sum of truly spam and falsely spam.
Exactly. It is detecting, your system is detecting as 150 spams, out of which all may not be spams. Only some may be spams. So basically 100 are not spams. 150 minus 50 are wrongly detected as spams. 100 are not actually spams.
So, ma'am, 150 is TP plus FP, ma'am?
Yes, it is TP plus FP. It is the total that it is predicting. Do I need to repeat this again? This part should I repeat again?
No, madam. Please explain FN, false negative.
Okay. So again, your actual, now this was the predicted values, 150. Now let us come to the actual spams. So out of this, whatever this total number of mails, I'm not concerned with the total number of mails. Your actual spams are how many? 200. Right? And your detection system is correctly detecting how many? 50. Remaining 150, it is not even detecting it as spam, which are actually spams. So, your actual spams, what is your actual class? This row, not this column. This row is your actual spams. So, your actual spams, this total is 200. Right? So, your TP plus FN is given as 200. And how many could detect? 50. So what is your recall?
0.25. That is 1 by 4.
Which is 50 by 200 or 1 by 4 or 25%. So essentially your answer is, I don't know, why did I call this A? This should be A. Sorry, this should be A.
Option B will be the correct answer, ma'am.
How so? Actually, I have marked also B, but...
Yes, ma'am. B will be the correct answer. Actually, 200 spams. Means the actual positive are 200.
Yes.
If it is detecting 50, then it will be 50 by 200. So the precision is 50 by 200, which is 25%. And the spam detection will be 50 by 150.
No,
that is
not
33.
Really. Not really. See, precision is what? Precision is what? Denominator is what in your precision? The predicted value or the actual value?
In precision, the denominator is 50
value.
The
Predicted value.
The predicted value, right? And what is your predicted value?
150.
150. So your precision should be 50 by 150.
150.
Right? So it should be 33.33. Do you get my point? What is your actual? Which one is your actual? This one, this denominator, or this denominator? What is your actual positive?
Positive plus false negative.
This is your actual positive, right?
Yes.
This is your actual positive. So your 50 should be divided by your actual positive for recall. And what is your actual positive?
200.
200. So 50 divided by 200 is 25%. So A should be the correct answer. This has been mistakenly marked here, but A should be your correct answer. Could you follow what I said?
Ma'am, can you explain recall?
Yes. Recall is the true positive value divided by the total actual positive value. So your actual positive value is the sum of this whole row. Whereas predicted positive value is your sum of this whole column. See, this is your predicted class. This is your actual class. So in your actual class, the positive row is this plus this. These two combined is your actual positive values. The ones that it can detect and the ones it cannot detect. Right? Whereas in your predicted class, these are your predicted positive values. The ones which are actual positive and the ones which are not positive yet detected as positive. So this is the actual summation and this is the predicted summation. So for recall, you have the denominator as the actual summation, which is true positive plus false negative, which is this. So actual summation is given as 200 in the question. The actual number of spams is 200, out of which it has detected 50 correctly. Remaining 150 it did not detect as spams. It detected 100 other spams which were actually not spams. So a total of 150 spams it detected, out of which 50 were correctly detected. Rest 100 does not belong to these 200. Rest 100 is actually belonging to the rest of the non-spam emails which it detected. Could you understand?
Yes, ma'am.
Is there any confusion?
No, ma'am.
No, ma'am.
Okay, so if that is clear, then the correct option should be A. I will change the slide for your understanding. That is all for today.
Ma'am.
Yes?
So, in the assignment, if we keep option A is right, even though that is right, 2 marks will be deducted, no ma'am, for evaluation.
Is it?
Because
Is it showing it as the wrong answer? I have marked what is given in the assignment, but if you see the conceptual understanding, then it is actually wrong. A should be the answer, right?
Answer. So, but we lose the marks, no ma'am.
Yeah. So I will just point it out to the illustrator. I hope ma'am will consider this. She will correct this and change it actually. But A should be the answer.
Okay, ma'am. Okay.
Ma'am, you can resubmit now. Tomorrow is the last day, right? You can resubmit.
Yes, ma'am. 10th is the last day of submitting the assignment, ma'am. 10th of August.
Okay, so you still have time for submission, right?
Yes, ma'am.
Okay, no problem. I will just bring this to ma'am's knowledge and she will probably change the answers so that you are not marked wrongly.
Okay, ma'am. Thank you.
Okay, thank you.
Thank you, ma'am. Thank you.
Thank you.